Now, it's pretty widely recognised that SLS, or Space Launch System, has become a bit of a nightmare for NASA, and there's a lot of fair criticisms of SLS. Almost every element of the project has gone completely pear-shaped, and NASA's copying a lot of criticism over all of it. But is this fair? Are the failures of SLS completely the fault of NASA? So to start understanding what the hell has gone wrong here, we need to start at the beginning, and that is with the Constellation program. Now, in the early 2000s, NASA had its sights set on a couple of clear targets: return to the moon, take humans to Mars, and to do this, develop a vehicle that could carry humans deeper into space than we've ever gone before. And this ambitious plan was called the Constellation program. The Constellation program was born in 2004 under the George W. Bush administration as part of the Vision for Space Exploration program. Now, this directive was born in the wake of the Space Shuttle Columbia disaster. The United States needed a new spaceflight program that could safely replace the aging and super expensive Space Shuttle program and reach for and achieve exciting new goals that would get the public all jazzed up about space again. These goals, as set out by the directive, were: 1, return humans to the moon by 2020, 2, develop systems for human exploration of Mars, and 3, create a robust transportation infrastructure for space exploration. Now, NASA's plan included the development of 2 new rockets, the Ares 1 for crewed missions and the Ares 5 for cargo. A brand new crew vehicle would also be developed, the Orion capsule. This would ferry astronauts to the moon, and a brand new lunar lander named Altair would complete the journey to the lunar surface in much the same way the command module and the LEM did for the Apollo missions. Now, initially, the Constellation program was estimated to cost about $230 billion through 2025. These projections very quickly ballooned as NASA began the process of turning plans into reality. Now, you need to remember this was also happening in the mid to late 2000s, an era where government spending was practically dominated by the Iraq War, Afghanistan War, and the enormous bailouts following the 2008 financial crisis. The initial budget for Constellation was $9 billion per year. However, once the reality started to set in for NASA, it became clear the actual cost demands of the project were closer to $15 billion per year. Underfunding meant delays, constant design revisions, and started leading to a perception of a seeming inability from NASA to meet the goals and deadlines set by US policymakers who obviously control NASA's budget. The other major and important factor here is NASA receives a flat yearly funding, which is not ideal for large projects, where the majority of the cost is incurred in the early stages where development costs are the highest. Let's get into the actual tech specs of the Ares lift vehicles because they are really impressive. Now, the crown jewel of the Constellation program was the Ares 5 heavy lift rocket, designed to carry massive payloads into space. This vehicle had a height of 116 meters, a diameter of 10 meters, and a payload to low Earth orbit, or LEO, of 188 metric tons, and a payload to translunar injection, TLI, essentially moon orbit, of 71 metric tons. Now, in terms of engines, the Ares 5 was to have 5 Rocketdyne RS-68B engines in the core stage, with 2 5-segment solid rocket boosters derived from the shuttle, and a single J2X engine in the Earth departure stage, or the stage that essentially heads off into space towards the moon. The Ares 5 was to be the workhorse of the program, capable of delivering heavy cargo to lunar orbit and beyond, and the Ares 1 being the crew transport vehicle. Now, the engines on the Ares 5 particularly deserve a little bit more detail than just to be brushed past, especially the RS-68, because the specs on this were impressive. The RS-68B was a modified version specifically developed for NASA's Ares 5 rocket. The B variant was optimized for performance and reliability for deep space missions. Now, if you're familiar with the RS-25, the earlier engine that powered the space shuttle, and now powers the SLS, sometimes called the SSME, short for Space Shuttle Main Engine, you might be thinking, well, this seems like a backward step to make the RS-68 open cycle, or gas generator cycle, compared to the closed cycle RS-25, the closed cycle being a far more efficient system. The reasons for this come mainly down to complexity. The RS-25 is notorious for being a highly complex engine, mainly due to its closed cycle reusable design. To put it as simply as I can, so this video doesn't end up being a 40-minute explanation of the minutiae of open versus closed cycle rocket engines. Basically put, open and closed cycle rocket engines use turbopumps to force fuel and oxygen into the combustion chamber at high pressure. More pressure in the combustion chamber equals more thrust from the engine. Now, turbopumps require a lot of power to operate, Where do we get that power? Well, both open and closed cycle rocket engines employ the use of what are essentially little baby rocket engines to spin a turbine which powers the pumps. The idea is burn a little bit of fuel and oxygen in a simple small rocket engine, point the high velocity exhaust of that engine at a turbine, and use the extremely high rotational force generated by this to power the turbo pump. Similar to how a turbocharger works in a car, using the exhaust gas from the exhaust of the engine to spin a turbine to create additional power. Now, an open cycle rocket engine dumps the exhaust from this little baby rocket engine, called a gas generator, over the side of the engine once it's gone through the turbine. Now, the reason for this is usually run really fuel rich in this small rocket engine to keep the temperature down so it doesn't melt the pump. The reason it's dumped over the side is if we were to plumb that exhaust gas after it's gone through the turbo pump back into either the combustion chamber or even the exhaust of the main engine, there's a very high likelihood, because it's fuel rich, it burns dirty, that it's going to coke up the injectors or just generally cause the main combustion chamber to run less efficient. Now, this wastage is not particularly good for the efficiency of the engine. It's a trade-off. Use some fuel and oxygen to power the pumps to get exponentially more power from the main part of our engine. Now, a closed cycle rocket engine operates by a very similar process. However, for reasons that are far too complicated to explain in a couple of minutes, the exhaust from the little baby rocket engine, in a closed cycle engine it's called a pre-burner instead of a gas generator, is then fed directly through the pumps and into the combustion chamber. Essentially, it's not dumped over the side and wasted. Because it all ends up in the combustion chamber anyway, we're not actually throwing away any of the chemical energy in the fuel over the side of the engine like we are in an open cycle engine. Now, if all of that went way over your head, don't worry. All you really need to understand is that open cycle engines lose a little bit of efficiency because they have to waste a significant portion of their fuel to power the pumps. Closed cycle engines, however, waste far less, so their efficiency is better. But this comes at the cost of a lot of complexity. More complexity equals more cost. Now, due to its open cycle design, the RS-68B had 80% fewer parts than the closed cycle RS-25. And likewise, the cost was 1/5 of the RS-25. When adjusted for inflation in 2025, the cost of the RS-68 is around $31 million per engine, whereas the cost of the RS-25 is $156 million per engine. Now, in space travel, cost and complexity are pretty important, to say the least. Now, this is why, for instance, the SpaceX Merlin engine that powers the Falcon 9 is open cycle, not closed cycle. The main goal of SpaceX when developing the Merlin engine was to make the engine as cheap and simple as possible. We can see pretty clearly that that approach works quite well. Okay, so the RS-68 was far simpler and far cheaper to build than the RS-25, but what about its performance specs? Let's have a look at these from the RS-68B, again using the RS-25 as a comparison point. The performance specs on the RS-68 are as follows. 758,000 pounds of thrust at sea level, or up to 860,000 pounds in a vacuum, in space, and a specific impulse, or ISP, of 365 seconds at sea level, or 410 seconds in a vacuum / in space. Now let's compare that to the RS-25, which has 416,300 pounds of thrust at sea level, or up to 512,300 in a vacuum, and a specific impulse, or ISP, of 366 at sea level, or 452 in a vacuum. Now, if that wasn't too many numbers thrown at you too quickly, you've hopefully noticed that the RS-68 has quite a bit more thrust than the RS-25. Now, this is primarily because the RS-68 was designed to prioritize maximum thrust, whereas the RS-25 was designed to prioritize efficiency, reusability, and lightweight. So to be fair, we need to also compare the thrust-to-weight ratio between these two engines. Now, the RS-68 has a thrust-to-weight ratio of 47:1, whereas the RS-25 has a thrust-to-weight ratio of 73:1. Now, given that you'd need more RS-25s though to equal the same amount of thrust, in the case of a rocket like the Ares 5, it sort of evens out, not quite, but close-ish. Now, the impressive thing about the RS-68 engine wasn't the amount of thrust, wasn't even the relatively high ISP or the price tag, it was the combination of the three in one engine. The bang for buck with the RS-68 was really impressive. Imagine an engine with more thrust than an RS-25, nearly as high of an ISP, and you can have 5 of them for the price of a single RS-25. You might be jumping ahead here and thinking, okay, well, why is SLS using RS-25s and not RS-68s, as was originally planned for the predecessor, the Ares 5? We'll get to that in a little bit, don't worry. Now, when we get to the Ares 1, the crew transport vehicle in the Constellation program, NASA instead went with a solid rocket booster for its first stage. Why? SRBs are cheap, simple, and reliable. Now, given there were some challenges involved with this decision, to be fair, there are challenges involved with all rocket development. That's why they call it rocket science. A mock-up test of the Ares 1 did fly in 2009, called the Ares 1X, which was a successful proof of concept. Now, as for how cheap the first stage SRB was on the Ares 1, roughly 70 to 80 million per launch for its 5-segment design. Now that still sounds like a lot of money, but relative to other crew-rated vehicles, it's pretty cheap. Remember, that's half the price of a single RS-25 engine, and SLS has 4 of them just in its first stage. Now, splitting up the crew and cargo vehicles for the Constellation program, I think was a really clever idea and a great and simple solution to reducing the overall costs, as it meant the RS-68 engine didn't have to go through the crew rating process, which is the process that any rocket engine has to go through before it can be approved for launches with humans aboard. It was also clever because it utilised existing SRB infrastructure from the shuttle SRBs. Now, coming to the Orion spacecraft, which sat atop the Ares 1 lift vehicle, despite delays and funding issues, NASA had successfully completed much of the design, prototyping and testing of the Orion as part of the Constellation program. The relatively advanced maturation of the Orion capsule is a major part of the reason why it was brought over to be part of the now Artemis program. While the Orion at a glance looks pretty much like an Apollo command module, every element has been drastically updated, except for the heat shield. They kept the same heat shield, and it's cracking, causing major delays in SLS. Why? Anyway, moving on. It also has 30% more habitable space for the crew than the Apollo capsule to help accommodate a crew of 4, 1 more than the Apollo missions used. Now, the Altair lunar lander, which was the lunar lander for the Constellation program, is a bit of a different story. It was far less advanced in development, still in the preliminary design phase in 2010 when the Constellation program was canned, though NASA had spent between 300 and 400 million US dollars on its development up to that point. This sounds like a crazy amount of money for a vehicle for which no actual flight hardware had been built, but it comes back to what I mentioned earlier about NASA's flat funding model not being well suited to spacecraft development. A disproportionate amount of the cost of developing a space vehicle is concentrated in the early stages of development. Much of the Altair's groundwork had been done. Unfortunately, to the untrained eye, with no flight hardware to show for it, this very much looks like a huge waste of money. When we get to 2010, the Obama administration made the decision to can the Constellation program. An independent review panel found that the program was unsustainable under current funding levels. It was years behind schedule, over budget, and according to this panel, unlikely to meet its goals of a lunar landing by 2020. Now, the political climate at the time played a key role in the cancellation of the Constellation program. It was argued that the program was more about maintaining jobs in certain states than achieving actual progress in space travel. Instead, the administration redirected NASA's efforts towards developing commercial spaceflight partnerships and planning for Mars under a more flexible timeline. Now, we're getting into the opinion zone here on a complex topic, but it's hard to see the cancellation of the Constellation program being more than an almost purely political decision. The program was a holdover from the previous administration. It was over budget and behind schedule, sure. But when has NASA ever been on budget and on schedule? Now, it's at this point of the story of the Constellation and Artemis programs that political interference really starts to muddy the gears of NASA. Now, this isn't a this side versus that side thing. It's more a story of political intervention taking precedence over actual progress in space. NASA had a pretty good idea of what they were doing with the Constellation program. They were given a goal and they set themselves to achieving it. Artemis is a totally different beast altogether. NASA wasn't given anywhere near as much of a blank slate to do their job. Instead, much of the program was dictated to them by policymakers who are not engineers, not rocket scientists, who have never put their hands to a single piece of spaceflight technology in their life. Now, to make my case here, we're going to talk about Artemis, the design decisions and parameters that were dictated to NASA, and how this has landed the program where it is today. Now, after the Constellation program's cancellation in 2010, the Obama administration refocused NASA on deep space exploration. Groundwork for Artemis was laid down with the NASA Authorization Act of 2010, which mandated the development of the Space Launch System, or SLS, paired with the Orion spacecraft and the Lunar Gateway, essentially a space station which would permanently orbit the moon and operate as a base of operation for moon landings. The Altair lunar lander was to be completely scrapped. NASA was to award a contract to a commercial contractor to develop the HLS, or Human Landing System, under its Next Space Technologies for Exploration Partnership, or Next STEP. Essentially, the SLS would take the Orion spacecraft to space. The Orion spacecraft would then take the astronauts to the Lunar Gateway, and then the HLS, or the Human Landing System, would then ferry them from the Lunar Gateway to and from the lunar surface. Now, 2 HLS contracts were awarded, one to SpaceX, obviously, to use their Starship as one of the lunar landers, and the other to Blue Origin to develop their Blue Moon lunar lander. It's a bit of a silly name, that, since lunar also means moon, so it's the Blue Moon lander. Come on, Blue Origin, do better. So in 2019, under the Trump administration, Artemis was officially unveiled with a directive to land the first woman and the next man on the moon by 2024. However, delays and funding constraints have shifted the timeline to 2025, then to 2026. Now, as of the time of writing this video, NASA has stated the crewed landing will take place no earlier than mid-2027. Even this timeline in 2027 is extremely optimistic given the challenges that Artemis is currently facing, and they are numerous. Artemis has 3 primary goals. Now, firstly, return humans to the lunar surface and explore areas never before visited by humans, such as the lunar South Pole, which is rich in water ice. Secondly, establish a sustainable lunar presence by building infrastructure like the Lunar Gateway and surface habitats, i.e. a moon base. And thirdly, use the moon as a testing ground for technologies and techniques needed for future exploration of Mars. Now, at the heart of the Artemis program is the Space Launch System, or SLS, the most powerful rocket NASA has ever developed to date. And under the current development, SLS has 2 different configurations, Block 1 and Block 1B, and the specifications for each are as follows. SLS Block 1 stands 98 meters tall, has a lift capacity to LEO, or low Earth orbit, of 95 metric tons, and a payload to Lunar Transfer Orbit, or LTO, of 27 metric tons. The core stage is powered by 4 RS-25 engines repurposed from the Space Shuttle program, each generating 512,000 pounds of thrust, as well as 2 5-segment SRBs, or solid rocket boosters, as we discussed earlier, derived from the Space Shuttle to provide additional thrust at liftoff. The upper stage, or ICPS, standing for Interim Cryogenic Propulsion Stage, uses a single RL-10 engine. SLS Block 1B is the big brother of Block 1 that stands at 111 meters tall, has a lift capacity to LEO of 105 metric tons, and a payload to LTO of 38 metric tons. The core stage of the Block 1B is the same as Block 1. The difference is in the upper stage, or EUS, meaning Exploration Upper Stage, replacing the Block 1's ICPS. It has 4 RL-10 engines for the more complex hardware required for an actual moon landing. Now, different to the Constellation program's approach, the SLS is designed to carry both humans and cargo payload to space, with the HLS module, essentially the lunar lander, to launch separately, provided by one of the 2 commercial contracts, either SpaceX and Blue Origin. Okay, so now I have a pretty good understanding of what Artemis and SLS actually is. Now we get to the problems. The reality is that SLS was doomed from the very start. It was greenlit in 2020 under intense political pressure to preserve jobs and expertise from the Space Shuttle program. NASA was mandated to use legacy shuttle components like the RS-25 engines and the shuttle-derived SRBs to maintain workforce continuity. Basically, it was used as a government jobs program. Now, if you remember from earlier, that was the very thing that Constellation was criticised for. This approach was very obviously about securing congressional support. The funding for Artemis and SLS essentially came with a bunch of poison pills designed to get political wins at the cost of actual progress in space. It locked NASA into outdated technologies and design choices that don't make any sense outside of the political environment that they were made. The result? To date, the Artemis program has cost over $93 billion, with each SLS launch estimated at $4.1 billion. Now remember, that $4.1 billion is just for the SLS and Orion capsule, which only gets astronauts to the Lunar Gateway, which is projected to cost another $10 billion. And then we have to add the cost of the HLS to actually get the astronauts to the lunar surface. And this is estimated to cost another 1 to 1.5 billion per mission. Now, given the Lunar Gateway is expected to be good for at least 10 missions, dividing this out still puts the total cost of each Artemis mission at around 6.6 billion US dollars. I should mention as well, these are just the physical hardware costs per mission. Now let's compare that to the Constellation program. The approximate cost of the Ares 5 per launch in 2025 dollars adjusted for inflation was around $2 billion. The cost of the Ares 1 being around $1.3 billion, and the cost of the Altair lunar lander about another $1.3 billion. This gives the Constellation program a total hardware cost per mission of around about $4.6 billion. That's 30% cheaper than Artemis. You know what really blew my mind when I was researching this video? The total hardware cost of Apollo missions was only $2.1 billion per mission in 2025 dollars. So how the hell is Artemis so expensive? Well, this is where we start getting into the specifics of those poison pills in NASA's Artemis funding I mentioned. We'll go through them one by one. Since I mentioned them earlier, let's start off with the SLS main engines. Congress mandated that NASA use the RS-25 engine over the RS-68 that they had intended to use for the Ares 5. Now, it depends who you ask, but my understanding from fairly in-depth research was the thought process of policymakers was twofold. Reusing old shuttle engines would save money by utilising existing leftover engines that could be cannibalised from the shuttle fleet. And it would also provide jobs through funding to key government contractors, such as Rocketdyne, to both refurbish and recertify these old shuttle engines, as well as build brand new RS-25s to make up the difference between how many old engines NASA had laying around and how many they'd actually need for all 6 Artemis missions. Now, one of the first problems with this is the refurbishment cost for the old shuttle RS-25s is $40 million per engine. $40 million just to refurbish an old shuttle engine. That's $9 million more expensive than a whole brand new RS-68 just for the refurbishment. Now, add to that the 24 brand new RS-25s that NASA had ordered, coming in at a cost of $146 million each. Now, it doesn't take very acute math skills to work out this is a false economy. If it costs more to refurbish a nearly 50-year-old RS-25 than it does to buy a brand new, significantly more powerful RS-68, obviously you choose the brand new RS-68. And the stupidity of this decision doesn't stop at just the cost. As we went into earlier, a large part of the cost and complexity of the RS-25 is due to the prioritization of reusability, which is completely wasted on a vehicle like SLS, which is single use. Every single SLS launch, there goes another $546 million worth of advanced reusable RS-25 engines completely obliterated and wasted when they smash into the ocean at 800 k's an hour. The RS-25 was never designed to be an expendable engine. The whole trade-off of the exorbitant cost was that it would be spread out across many shuttle missions. It's a totally inappropriate choice for a rocket such as SLS when there are cheaper, more powerful rocket engines available which are specifically designed to be used on expendable vehicles. Now, to be totally fair here, there are some decent arguments against the use of the RS-68 for SLS. Really, these come down to 2 main arguments, which I'll address one at a time. Firstly, the RS-68 engine isn't crew rated, meaning it hasn't gone through the approval process I mentioned earlier to be used on launches with humans aboard. Now, this is a large part of the reason the Ares 1 used an SRB for the core stage, as the shuttle SRB system was already crew rated. It is true that this would likely be a lengthy and expensive process. There would no doubt have to be many small changes made to the engine to get it over the line for a crew rating. To balance that though, the RS-68 has a flawless flight record with 74 engines successfully flown across 44 missions with the Delta IV Medium and Delta IV Heavy. As for cost, while it would no doubt be expensive to get the RS-68 crew rated, the difference in cost between the RS-68 and the RS-25 is still so astronomical, it would almost certainly still lead in the favour of the RS-68. The total program engine cost for SLS's 16 refurbished and 24 brand new RS-25s is $4.1 billion. If NASA were to instead order 40 brand new RS-68s, this would only be $1.2 billion. That leaves $2.9 billion left over in the kitty to crew rate the RS-68s just to break even against the cost of the RS-25. Now, keeping in mind that while not yet officially funded, NASA is expecting the Artemis missions to be funded past Artemis 6, meaning the development cost for the crew rating on the RS-68 would be spread across more missions, reducing the cost drastically over time. Now, I do have to mention, even though the RS-68 has more thrust than the RS-25, in the case of SLS, due to the RS-68's higher fuel consumption and slightly lower efficiency, it's mostly agreed that the SLS to use RS-68s would need to employ the use of 5 to achieve the same payload as 4 RS-25s. I know it seems weird, but the math on this does check out. Even with the extra engines though, to make up 5 for each Artemis launch, this still only brings the figure up to 1.4 billion for 46 RS-68 engines, leaving 2.7 billion and change from the RS-25 price. So we still end up way out ahead with the RS-68s over the RS-25s. Now, the second decent argument against the use of the RS-68s for SLS is the engine's limited ability to withstand the heat generated by its close proximity to the SRBs. The RS-25 is a regeneratively cooled engine, meaning it uses the extreme cold of its cryogenic fuel to cool the combustion chamber, throat and nozzle of the engine. Now, it does this by passing liquid hydrogen through cooling channels which surround the critical parts of the engine. This drastically reduces the heat load on the engine. In the case of SLS, it also protects the engine from the intense heat generated by the 2 SRBs, which are located right next to the main engines on the core stage. Now, the RS-68, however, for simplicity's sake, employs the use of ablative cooling rather than regenerative cooling. The inner surface of the nozzle is coated with a carbon phenolic material, which is designed to essentially burn off over the burn time of the engine, taking the heat out with it. This works in a very similar way to how the heat shield on a capsule-style spacecraft protects the crew on re-entry. Interestingly, if you watch a Delta IV rocket launch, which uses RS-68 main engines, you'll notice an orange tint to the exhaust of the engines. Now, Hydrolox rocket engines, which the RS-68 and RS-25 are, which run on liquid hydrogen and liquid oxygen, generally burn almost completely clear as they have an extremely clean burn. The orange tinge on the RS-68, however, is actually the carbon phenolic coating burning off. Now, the RS-68 engine not being able to handle the heat of the SRBs during launch is probably the #1 argument that I've seen made against the use of this engine while researching this video. Rocket science and engineering is the art of problem solving and compromise on an extreme level. Now, personally, I think the idea that this problem couldn't be solved is ridiculous. I'll admit I'm not a rocket scientist or a rocket engineer, so I found some ideas from people who are to solve the heat issue. NASA actually put up this animation of an alternative engine arrangement for the Ares 5, which pretty much solves the issue by spreading out the engines away from the SRBs. And this is just one of the many potential solutions that I found by a simple Google. So look, my point here is this is almost certainly a solvable problem for the RS-68. This one here is perhaps the most face-palmable problem with SLS. A mobile launcher platform is essentially the stand that NASA uses to stack, test, move, and launch their vehicles. Mobile launcher platforms, or MLPs, have been used by NASA since the Apollo era. Now, when it comes to the MLP for SLS, instead of the MLP essentially being just a large land barge that moves the rocket to and from the launch tower, the SLS's MLP have an integrated launch power built onto the platform. Artemis 1 launched from Mobile Launcher 1, or ML1, a modified version of the MLP which was built for the Ares 1, the crew transport vehicle under the Constellation program, which we discussed earlier. The SLS Block 1B, the first SLS rocket capable of actually supporting a moon landing, requires a significantly larger MLP, or the Mobile Launcher 2, or the ML2 as it will be called. The contract was awarded to Bechtel in 2019 for a cost plus value. When will NASA learn with cost plus funding? But anyway, of $383 million. Cost plus contracts, if you're unfamiliar, essentially guarantee a profit to the contractor, meaning any cost overruns are covered by NASA, so the contractor will profit regardless of the final cost of the project. Now, this obviously doesn't incentivize the contractor to keep the project to budget, and massive cost overruns are basically par for the course with cost plus funding. In the case of ML2, Mobile Launcher 2, for the Block 1B variant of the SLS, the $380 million budget has now ballooned out to an expected $2.7 billion. On top of that, the expected completion date is also 4 years behind, with its original 2024 completion date now pushed out to 2028 at the earliest. Now, NASA's use of cost plus contracts has long caused them headaches, It looks like they're maybe now finally moving away from this. Probably a couple decades too late, but whatever. Now, the contractor Bechtel's version of the story is that COVID and inflation-related price increases and challenges, as well as NASA's revisions to the project, have caused the price to increase by more than 7 times. I don't buy that. 7 times increase. Now, regardless of whether this is a ridiculous excuse for a 7-fold increase, COVID-related inflation and effects definitely equate for at least some portion of that sum. When the Obama administration cancelled the Constellation program, not only did they throw away $9 billion worth of work, but they also set NASA back at least 5 years, with NASA having to almost completely start again. Now, I'm not pretending that I have a magic viewport into an alternate timeline where Constellation was never cancelled. However, it's highly probable from the evidence available that the ML2 platform for Constellation would have been completed prior to 2020 had it not been cancelled, missing all of the COVID-related costs, overruns and delays. Now, the Obama administration obviously couldn't see into the future either, but delays have consequences. Now, as for the flat funding model, I've touched on this a couple of times so far, but this subject deserves a little more explanation as it does trail off the last point. Let me explain. Now, as I mentioned before, NASA receives its funding from Congress in a flat yearly sum. And because a disproportionate amount of cost is concentrated in the early stages of a program's development, NASA has to be quite selective in prioritizing which parts of development start first and which parts they can delay significant funding to. It takes a little bit of time for NASA to ramp up. They can't hit the ground running. This is why, for instance, in the case of the Constellation program, the Ares 1 and the Orion spacecraft were so far along in maturation, but the Altair lunar lander and Ares 5 were quite a bit further behind. The human flight systems were the priority, as they were the most technically challenging, but also had the highest consequence in the event of failure. When Constellation was cancelled, the rug was pulled from underneath NASA. All the early development work was thrown away with the exception of the Orion spacecraft. The clock was set back to zero. The slow and arduous task of getting the ball rolling was started again, right as the Constellation was getting off the ground, quite literally in the case of the Ares 1. Yet again, NASA was given a very difficult task with a limited trickling budget and a very ambitious timeline, and then when it predictably all turns out badly, the blame is pinned on NASA. This is not a recipe for success, it's a recipe for failure. Now, to be really clear, I'm not arguing that NASA is a perfect organization. That would be totally ridiculous. But it is important to recognize that they act in accordance with what they're given. Now, I would argue the story of Constellation and Artemis is more a story of a government that doesn't know how to handle or fund its space agency than it is a story of a space agency that doesn't know how to meet the goals that it's given. Some of this stupidity is just baked into the cake with a government-funded agency. Inefficiency, high cost, delays, etc. A private company can do whatever it wants. The development of SpaceX's Starship is a great example of this. SpaceX has the ability to build fast, fail, and rapidly iterate as much as they want. If they blow up a Starship, which they have, no one bats an eye. If NASA were to blow up a single SLS vehicle, they'd be brought up before a congressional hearing in a heartbeat and raked over the coals for wasting public funds. All of that being said, when NASA is left alone to do the job they've been given, to do the job that they have decades of expertise in, they have proven over and over that while late and expensive, they can get it done. As a space enthusiast and a lover of space exploration, harbour and engineering, when I look at the Constellation program, I get excited. 2 new vehicles for NASA, a far more cost-effective method of crew transport to space, and an Ares 5 rocket able to deliver massive payloads both to the moon and beyond. When I look at SLS, however, all I see is disappointment. The Block 1B of SLS has a max payload to lunar orbit of only 42 metric tons. Even the planned Block 2 SLS, which is meant to be bigger again, only has a max lunar orbit payload of 46 metric tons. I don't know if SLS will be cancelled. I think it probably should be. It doesn't make sense to launch a crew on an SLS to the Lunar Gateway for transport to the lunar surface when the Starship HLS is going there anyway and could just take them straight there. This whole program doesn't make sense anymore. And the most frustrating thing to me is that the Constellation probably would still have as a transitional vehicle until Starship and New Glenn were fully operational. If you've gained anything from this video, I hope it's a little more grace for NASA and a little bit more understanding of the position they've been put in. I don't hate SLS. It's still a beautiful vehicle. To me, any vehicle built by NASA is going to be a beautiful vehicle. Any vehicle capable of putting any payload into space is a beautiful vehicle, because I love space exploration engineering. For me, it's just ruined because SLS is technology that would have been great 20 years ago. Anyway, that's mission success for me. I know this was a longer one, but if you think I've missed something, gotten something wrong, or have something you'd like to add, please let me know in the comments. If you liked or found this video interesting, help me out by giving me a subscription. It helps me out, but it also means that you won't miss out on any of the whole bunch of space-related content I have coming down the pike. Anyway, that's it for me. Thanks for watching, and I'll see you next time.